Hello Year 12. Today we're looking at applications of the normal distribution. So the normal distribution is often used in quality control and predicting outcomes. So we have some examples here today. And the first example is a company produces 1 kilo packets of sugar. A quality control check found that the weight of the packets was normally distributed with a mean weight of 0.995 kilograms and a standard deviation of 0.03 kilograms. The company policy is to reject any packet that with a weight outside 2 standard deviations from the mean. So we want to work out what the smallest weight is allowed by the company. So the smallest weight is 2 standard deviations below the mean. So it will be the mean minus 2 standard deviations. So our mean is 0.995 minus 2 lots of our 0.03, which is our standard deviation. So 0.995 minus 2 lots of 0.03, which is 0.06. So 0.995 minus 0.06 is equal to 0.935. So therefore the smallest weight is 0.935. What is the largest weight allowed? So the largest weight allowed is 2 standard deviations above the mean. So we'll have our mean of 0.995 plus 2 lots of standard deviations above the mean. So this is 0.995 plus 0.06. So 0.995 plus 0.06 is equal to 1.055. Now we must answer this in kilograms because it is a weight question. So then, what percentage of packets will be rejected? So we need to think back to our normal distribution graph, and that is on our reference sheet. And with our reference sheet, it said that 2 standard deviations was above and below the mean is 95%. So about 95% of weights lie within 2 standard deviations. Standard deviations of the mean. So this means that 5% will be outside of this area. So, the company rejects 5% of stock. Now we want to know what percentage of large packets will be rejected. So because this normal distribution is symmetrical, the 5% is made up of 2.5% above the mean and 2.5% below the mean. So the company will reject 2.5% of the larger packets. Okay, example 2, we have the mean shelf life of a spice is 13.4 weeks and the standard deviation is 1.8 weeks. Would a shelf life of 20 weeks be unusual? So what we want to do here is we want to work out what 3 standard deviations above and below the mean are, because if a shelf life of 20 weeks is above 3 standard deviations or below 3 standard deviations, that means it's very unlikely. So we have our mean equals 13.4. So our mean minus 3 standard deviations, and this is where our standard deviation is 1.8. So it will be 13.4 minus 3 lots of 1.8. 13.4 minus 3 lots of 1.8 gives us 8. So that means 8 weeks is the lowest on our scale, and then plus 3 standard deviations is 13.4 plus 3 lots of 1.8, which equals 18.8 weeks. So, yes, a shelf life of 20 weeks will be unusual, as the shelf life of most spices is between, actually let's change most to 95%, because that is 3 standard deviations. Oh, sorry, it's 99.7% actually. I was wrong on that one. So 99.7% of spices is between 8 and 18.8 weeks. And because it's outside of the range, it's not likely. Now we want to find the Z-score for a shelf life of 15.5 weeks. So we use our Z-score formula, which is Z equals X minus the mean over the standard deviation. This is on your reference sheet, remember? So we have X is our 15.5 minus our mean of 13.4 over our standard deviation of 1.8. So put that into your calculator. 15.5 minus 13.4 over 1.8 gives us a Z-score of 1.1666 ... which equals 1.17 to 2 decimal places. Now we want to know what percentage of shelf lives would be expected to be between 13.4 and 15.5 weeks. So what we're going to do is we're going to draw up a standard deviation. So we have that this is 13.4, and then we want to work out add our standard deviations onto our mean. So 13.4 plus a standard deviation of 1.8 means that this is 15.2 here, plus 1.8. This is 17 plus 1.8. This is 18.8. We earlier worked out that that was 8. 13.4 minus 1.8 means that this is 11.6. And this is 9.8. So our 15.5 would be roughly here, and our 13.4 is here. So we are talking about this bit here, which is 1.7 standard deviations above the mean. So what we need to do is we have that this bit here, is where our score of 15.5 is, and that is a Z-score of 1.17. So what we want to do is that we have the probability of 13.4 is less than or equal to X is less than or equal to 15.5. Now we want to turn that in terms of Z, so we're going to do the probability of 0, because the mean is 0, is less than or equal to Z is less than or equal to our Z-score of 1.17. So what this means is it's the probability of Z is less than or equal to 1.17 minus the probability of Z is less than or equal to 0. So what we need to do for this is we need our normal distribution table. So I'll just quickly pull mine up here. So we're looking for 1.17. So 1.17 is here. So it's 0.8790. We also needed a score of 0, so 0.5. So this will equal 0.90 minus 0.500, which equals 0.379. So 37.9% of shelf life, or shelf lives, would be expected to be between 13.4 and 15.5. So here, I'm just going to highlight here to say use normal distribution table. Oh, we forgot the L in table. Very good. So using Z-scores allows us to compare two data sets as well. So in our example, we have in year 7 at a school, the mean weight of students was 59.4 kilograms and the standard deviation was 3.8 kilograms. In year 8, the mean weight of students was 63.5 kilograms and the standard deviation was 1.7 kilograms. So John in year 7 and Doug in year 8 both weighed 68 kilos. Which student was heavier in relation to his year? So how we can do this is we can look at each student individually. So John and Doug, and we need to work out what their Z-score is. So whoever has the higher Z-score is going to be the one that is heavier. So we're going to substitute in. So John, he was in year 7 and Doug was in year 8. So when we're looking at that information, so we'll have John's Z-score, his weight was 68 kilos, minus the mean of his year was 59.4, and the standard deviation was 3.8. So John's Z-score, we put that into our calculator. We get 2.26315, 7895. And then for Doug, his weight was also 68 minus the mean of 63.5. over the standard deviation of 1.7. So 1.7, 63.5. So Doug had a Z score of 2.6470588824. So just going to round both of these to 3 decimal places. Okay, so a Z score of 2.647 is higher than a Z score of 2.263. So therefore, Doug weighed more in relation to his year group.